we are picking the names of our partners out of a hat. So instead of trying to have people match up themselves, we're just going up. All the boys are in a hat, girls pick the name. All the girls' names are in a hat, boys pick a name. Whoever decides to pick, that's the way it works. In his situation, there are boys picking the names of the girls out of the hat. There are 24 girls in the class, and excluding the ones who have boyfriends and the ones who have already made it clear that they do not want to dance with me, are to believe. That leaves 8 girls out of the class that I would like to dance with, that I think might, develop into a productive relationship or something. Who knows? Okay, so there are 8 girls left. Now, if I'm just going to reach into that hat and pull out a name, what is the probability that I will have one of those girls as my dance partner? What we have here is something called theoretical probability. Okay? Now the key terms in this are the outcome, which is the result of a single trial. In this particular situation, that's the girl's name that I pick. That's, I reach into the hat, I pick out a card, it has a name, that name is the outcome. The sample space is all the possible outcomes, all the names in a hat. All right? So every single one of those, all the girls in the class are part of that sample space. The event, what we're trying to find the probability of, the event is a particular outcome or a set of outcomes if I'm selecting more than one name. But in this situation, the event is basically what happens. I pick out a name, that's the event. What we're trying to find out is the probability of that event. So the probability of an event is defined as the number of favorable outcomes, meaning what you want to happen. In this case, I want one of those girls that does not already have a boyfriend and does not want to be, or does not already not want to be with me, divided by the total number of items in the sample space, which is all the girls in the class. So for this particular problem, the probability that I end up with a happy dance partner is 8 total girls that still would like to dance with me. They don't already have a boyfriend or they don't dislike me too much, out of 24 total girls in the class. So the probability that I end up with a great dance partner that makes, it's going to be a happy dance, is 8 out of 24, which can be simplified just like any fraction down to 1/3. Okay, we can simplify probabilities the same way we simplify fractions. So in this case, there's a common factor of 8 in both of those, so we can divide them both by 8. We end up with a probability of 1/3. It's about 33%, which means it is more likely that I do not have a happy dance partner than I do have a happy dance partner. So this is just your basic theoretical probability. Now, we don't know what's going to happen, but in theory, there's a 1/3 chance that I pick one of those girls. Now, here's another example. Let's say kids are lining up for playground balls to use at recess. These are elementary school kids, and instead of them all making a big run to get these things to play with, the teacher, to avoid fights, has decided that you get in line, and I just pick a ball out of the box and I give it to you, and that's the ball you play with. Okay, they're elementary school kids, they'll be fine. Anyways, they pick a ball right for each student to play with. The box has 7 soccer balls, 4 basketballs right there, 6 kickballs, 3 volleyballs. Now, if you count that up, that's a total of 20. We need to know that because that is our sample space. There are 20 total things that can happen. The event that I want to find the probability of in this case is the probability that I select the volleyball, or that the teacher selects the volleyball and gives it to me. Okay? So, the outcome I want is a volleyball. How many ways can that outcome occur? 3 ways, because there's 3 volleyballs. That's the number of favorable outcomes. The total number of outcomes, or our sample space, is 20. The probability I get a volleyball is 3/20. Not very likely. How about a basketball? Well, it's 4 basketballs. 4 basketballs. So the number of favorable outcomes for this event is 4. The total number of possible outcomes is still 20. There's still 20 balls in the basket, or the box, or whatever. So the probability I select the basketball is 4/20. Now, the reason I chose this one is because this can be simplified down to 1/5. This cannot be simplified. It's not always, but many times it's in your best interest to simplify just because you're dealing with smaller numbers. It's easier to picture. We're more used to a fraction like 1/5 than we are with 4/20. Now, as we get into compound probability and other things, you'll see that it might be necessary to leave it unsimplified, but that's for a later lesson. For right now, simplify when you can, okay? And there'd be simple fractions to simplify, nothing too complex. So there we go. Theoretical probability. Make sense? Sound good? All right, moving on. Now, let's say that I'm in line and I'll take a basketball, a volleyball, whatever other ball was there, I can't remember. Kickball, kickballs are cool, but I don't want a soccer ball. The soccer balls we have are not really good and they kind of hurt my feet and they're just, you know, the air is not, I just don't want a soccer ball. But I don't have any say in the matter. I get whatever the teacher gives me. So whatever happens, I do not want a soccer ball. What is the probability that I do not get a soccer ball? Now, there's two ways to do this. First way is to go back and say, okay, well, there's 4 basketballs, 6 kickballs, 3 volleyballs. That's 4 plus 6 is 10 plus 3 is 13. So there's 13 balls that will allow me to have a favorable outcome. 13 balls that are not soccer balls out of 20 total. So the probability that you not get a soccer ball is 13/20, which is good. Right? It's more than half. So it's more likely that I don't get a soccer ball than I do get a soccer ball. Okay, so that's the probability. Now to get that, I had to add those 3 numbers together. And in this particular case, it was not a big deal, but in other cases, it gets more complicated sometimes. So if you have to add a whole bunch of numbers, you might think, is there an easier way to do this? When you're looking for something, when you're looking for a selection that is not the favorable outcome. So instead of we want a soccer ball, we do not want a soccer ball. Or we do not want a basketball, we do not want. It's the opposite of something that we want. We call this the complement of an event. So one way to do it is to add up all the alternatives. But another way to do it is to do it this way. You can say the probability that we don't get a soccer ball is equal to 1 minus the probability that we do get a soccer ball. 1 representing 100% all the possible outcomes. So if you look at it this way, the probability that you do get a soccer ball, there's 7 soccer balls out of 20 total. 1 minus 7/20. If you don't remember, you're working with fractions. We find a common denominator, so that's 20. 20ths minus 7/20. You subtract the numerator for a total of 13/20. Now again, you might think, well, that was a lot more complicated than that. It depends on the problem, it depends on the numbers you're working with, and you start getting the hang of it subtracting from 1. You don't have to create that common denominator. Most people are able to do that in their head after some practice. And they're able to just say, oh, that's 7 soccer balls, which means 13 of the 20 are not soccer balls. And that's it. So that's referred to as the complement of an event. You'll see it written like this, probability of not a soccer ball, and sometimes you'll even see it written like this. With a line over top of it. That means not. Okay? So just in case you happen to run into that somewhere in your studies or your work or your textbook or something, that's the same thing as this, and it's the complement of an event. It's 1 minus the probability of that event. Okay? Here we go. Here's another example, just going back to the same thing. Let's say I'm in line and I want a tennis ball. What is the probability I'm going to get a tennis ball? Well, if you recall, there are no tennis balls. So the number of favorable outcomes, 0. Out of 20 total outcomes, and we know 0 divided by anything is 0. It's kind of a dumb problem. There's a point to it. What's the probability I do not get a tennis ball? Let's say I'm in line and I'm just saying, oh, I just don't want a tennis ball, I don't want a tennis ball. Well, guess what? There's no tennis balls. So that means that any one of those balls that I get is going to be favorable. So there are 20 ways for me to be happy in there. All right, there's volleyballs, basketballs, soccer balls, kickballs. There's no tennis balls. So all 20 of those playground balls are going to be favorable experiences. Out of 20 total, if I take 20 divided by 20, that gives me 1. Why did I do this? Because I just wanted to stress this point, that the lowest possible probability is 0. You will never get a negative probability. And the highest possible probability is 1. If you end up with a probability greater than 1, you did something wrong. Okay? You will not get a probability higher than 1 or lower than 0, and all possible answers are either going to be that, and all things in between. Okay? So that's just something to understand when you do work with probability. If you end up with an answer at 1.5, something went wrong. Okay? All right. Now, a lot of times you hear the word probability and you hear the word odds and you assume they're interchangeable. What's the probability this is going to happen? What are the odds this is going to happen? They're not interchangeable. No. Please be aware of that. Are probability and odds the same thing? No. All right, they have two very different definitions. They both use the same numbers. They use the same data, but they have different definitions. Let me show you. Once again, here's the probability of an event. Number of favorable outcomes, which you can refer to as the number of successes, the number of ways you can succeed. Okay, if I want a basketball and I get a basketball, that's a success. I'm feeling good. All right, over the total number of outcomes. Here's what the odds of an event is. The odds of an event are the number of favorable outcomes to the number of unfavorable outcomes. All right, I want a basketball, teacher gives me a basketball, that's great. I want a basketball, teacher gives me a kickball, I don't want a kickball. Although you can shoot hoops with a kickball, but you're not supposed to because it put a hole in it. We won't talk about that. So this is the odds of an event. Notice the odds of an event does not use the total sample space. It focuses on successes and failures. Favorable, unfavorable, good things, bad things. Okay, that is what allows us to do odds. Now let's take a look at how that works here. Note, recall from the previous example that a volleyball probability is 3/20. There's 3 volleyballs out of 20 total. If I would say what are the odds that I get a volleyball, that would be 3 volleyballs out of 17 non-volleyballs. There are 3 successes, there are 17 failures for a total of 20 total things. But what odds does is it directly compares the successes to the failures. The nice thing about odds is that you can see which is more likely, a success or a failure. In this case, the failure is much more likely than a success. There's many more ways to fail than to succeed. The nice thing about probability is you can turn probabilities into percentages. Okay? You can't really do that with odds. So, with odds, it's basically a direct comparison. A lot of times odds really aren't even written as fractions. They're often written as ratios, 3 to 17. Okay? And one thing to keep in mind, many of you hear about odds in terms of gambling. You hear about stuff on TV about the chances that this team wins the World Series, or 5 to 1, 8 to 1. Those are what's referred to as the odds of failure. That means the first number you see is not successes but failures. The second number you see is successes. So if someone's the odds of someone winning the World Series are 8 to 1, that means there's going to be 8 ways they fail, 1 possible success. So the actual probability they succeed would be 1 in 9 total outcomes, 1/9 chance. Okay? So that's something we'll get into in more detail if necessary. But there's the difference between probability and odds. Make sure we note the difference there. That's key. Okay? So if the probability of winning a particular game, whatever that game is 7/12, what are the odds of winning that game? Well, there's 7 ways to succeed. And there's 12 total things that can happen, which means out of those 12 things, 5 of them are failures. So 7 successes, 5 failures, for a total of 12. And again, by using odds, what you're able to do is you're able to see that it is more likely that I succeed than I fail. Successes occur more often than the failures do. Now, one thing to note, and this is key, odds can be greater than 1. I made a big deal about how probability cannot be. Odds can be greater than 1. All right, so that's important to keep in mind. All right, so if you end up with an odds of something on the numerator bigger than the denominator, it's okay. All right, one last thing to discuss, experimental probability. That's based on data collected from repeated trials, and here's essentially what that means. Let's say surveillance footage of 1,500 cars at an intersection. You know there's cameras at intersections now, a lot of places. Okay, if you didn't know that, when you guys start driving, watch it, just be careful. All right, showed that 673 of those cars did not come to a complete stop. Okay, so the purpose of this camera was to collect data. And over time, many days, weeks, whatever, depending on how busy the intersection is, they noticed that 1,500 cars came through this particular stop sign, and 673 of them did not come to a complete stop. They came to a rolling stop or whatever. Find the probability that a car does not come to a complete stop at that intersection. So based on the data that has been collected over repeated trials, 1,500 of them, we have come to the conclusion that approximately 673 out of 1,500, which instead of trying to simplify, when they get that big, we just turn them into a percentage. Approximately 44.9% of the cars do not come to a complete stop, almost 45%. Now what we can do then is we can use that to do a problem. We can say, okay, let's just say 200 cars come to that stop sign on a given day. How many cars do you expect? See, notice this was based on data from repeated trials that we saw happen. And we're going to use that to make a prediction. That's what probability does. The word probability has inside it the word probably. Okay? How many cars do we expect? How many do you think will probably not come to a complete stop? That's what probability is all about. What is probable? What might happen? We don't know what will happen. We're making a good educated guess on what might happen. So if 200 cars come to that stop sign, we expect about 44.9% of them to not come to a complete stop. That's about 90 cars out of 200. Now, one thing we can then do is we can then say, well, if these cars do not come to a complete stop, that means that 110 of them, because it's 200 total, will come to a complete stop. Okay, so we can make that assumption as well. Now, what does that mean? Well, maybe that means that this is a dangerous intersection. And this is why it's a dangerous intersection, because cars are not coming to complete stops. Maybe that means that that would be a good place to put a police officer. That might be a good way to allocate our funds and decide to put a police officer there instead of over there where most cars come to a complete stop. That's how you would use data to make judgments about where best to utilize your resources. Okay, this is one example. There are many others, so we will work on that another time. Thank you.